Frequency is how often a category or value occurs in a list of possible categories or values. This is a frequency distribution of number of cars by car color, a qualitative variable. The categories are nominal, without a natural order, so the category order is what you want it to be. In frequency distributions of quantitative data, the categories are numbers or intervals. These have a natural order, smallest to largest or largest to smallest. This frequency distribution is the number of pets kept by participants in a study. This is the frequency of commute time in minutes for 44 people. The categories are intervals with lower limits and upper limits, since a frequency table by individual minutes would be useless. Frequency can be changed to relative frequency. Relative frequency is the number of observations in a class divided by the total number of observations. Relative frequency can be expressed as fractions, decimals, or percentages. Relative frequency for any category has to be 0 or greater and not more than 1. The sum of relative frequencies must add to 1. Two other frequencies commonly used are cumulative frequency and cumulative relative frequency. Cumulative frequency is the successive sum of frequencies from top to bottom of the categories. The first cumulative frequency is the same as the frequency. The second is the first plus the second, and keep adding. The last entry should be the sum of frequencies. Cumulative relative frequency is the successive sum of relative frequencies. Start at the top and add as you go down the table, just like the cumulative frequency. The last entry should be 1, the sum of relative frequencies. Cumulative frequency and cumulative relative frequency aren't useful with nominal categories, like car color, that don't have a natural order. All of the frequency distribution types can be calculated from any one other type, if the total number of observations is known. Most frequency distributions for quantitative data have a range of values for each category, called the class limits. The range of values in a class is the class width. For the commute time data, the class limits are 0 to 9, 10 to 19, and so on. The class width is 10. Class width and the number of classes go together, and both of these are affected by the range of data values. Some people have very specific instructions about class limits, class width, and number of classes. These are easy to find if you want to use them. However, the utility of the frequency distribution is more important than any specific rule. Below are guidelines for class limits, class widths, and number of classes. First, choose a class width. Most class widths suggest themselves. Weight of people would usually be in 5 or 10 kilogram widths, so that a class can begin or end on a multiple of 5 or 10, depending on the range of the data. House prices would be in tens or hundreds of thousands. Car gas mileage would be in 5s or 10s. In particular, don't use strange class widths, like 7 kilograms for weight of people, or $13,300 for house prices. Unusual widths distract from the information presented. Use what can be quickly understood by an audience, so they aren't figuring out classes instead of paying attention to the presentation. Look at class width like speed limits. In Canada and the US, these are divisible by 5. There are no 58 or 37 speed limits. A Canadian speed limit of 70 kilometers per hour would be 45 miles per hour in the US, even though 70 kilometers per hour is equal to 43.5 miles per hour. Also, all classes must be the same width. Unequal class width means someone is lying to you. They want to emphasize some class at the expense of others, or bury some detail they don't want anyone to notice. For example, a notable Fox News frequency distribution of number of COVID cases has successive class widths of 30, 30, 10, 30, 30, 30, 50, 10, 50, 50, and 50. As a general rule, use between 4 and 12 classes. Fewer than 4 will probably not provide much information. More than 12 are hard to interpret. In particular, avoid breaking frequency distributions across pages. This may be necessary in some cases, but it is difficult to follow. Once a possible class width has been chosen, try it out. Divide the range of the data by the class width to see how many classes will be needed. Adjust the class width until a reasonable number of classes are reached. For example, suppose the weight of adults in a sample ranges from 35 kilograms to 160 kilograms. Reasonable class widths would be 5 or 10. A class width of 5 would have 25 classes, which is too many. A class width of 10 is about 13 classes, a more reasonable number. A class width of 20 may be even better. Class limits are the lower and upper values of classes shown in the frequency table. They should be whole numbers if possible. The smallest observation determines the lower limit of the lowest class. That observation can be at the lower limit, such as when a 0 is present, or in the middle of the class, as convenient. If x is the lower limit of the lowest class, then the upper limit of that class would be x plus width minus 1. Then add the class width to each of the previous class limits. For example, if x is 30 and the class width is 3, the class limits would be 30 to 32, 33 to 35, and so on. Class boundaries are the actual cutoff values that separate the classes. The class boundaries will coincide with the class limits if there are no decimal values in the data. Decimals in the data require more specific class boundaries. A good approach is to begin the lower limit at 0.6 and end the upper limit at 0.5, as shown in the table. The main point to remember is that every observation must go in a class, and must go in only one class. There must be no gaps or overlaps. Some calculations require class midpoints. The class midpoint must represent the class and be easy to use and interpret. In fact, a better name is representative value, but midpoint is shorter. There are many ways to find midpoints, such as averaging successive lower limits or averaging the lower and upper class limits. If these result in a useful midpoint, then use them. However, a formula is less important than representing the class. Choose a value that is meaningful for the classes and is easy to use. For example, a calculation may give a midpoint of 15.25. It may be correct, but it isn't as useful as 15. Avoid fractions if possible. Midpoints represent the class, but don't have to be exact. In fact, it is virtually impossible to find midpoints that are mathematically or statistically correct. The distribution of values in any one class will be different than that of any other class. As an example of preparing a frequency distribution, the data below are commute time in minutes for 44 people. The minimum is 0 and the maximum is 67. For this data, a natural class width is 5 or 10. A class width of 5 minutes will have 14 classes. This might be reasonable if there were more data in each class, but there are only 44 observations. A better choice here is a class width of 10 with 7 classes and 6 or 7 observations per class. The lowest class should include the 0 in the observations. A class width of 10 with the lowest valued 0 would have class limits 0 to 9, 10 to 19, 20 to 29, and so on. Class boundaries can coincide with the class limits since there are no decimals. With these class limits, this is the frequency distribution. Convenient midpoints are 5, 15, 25, and so on. These midpoint values represent each class adequately. In this case, the midpoint is the average of successive lower class limits. In fact, the actual average value per class and the midpoints only match for one class. Also, the distribution of values in each class are not alike.